Far Uvc radiation technology. We want to present the current state of knowledge as understood by the IUVA panel of technical experts. Mickey, next slide, please. This is in keeping with our vision. Since IUVA is a 501c3, we do want to note that we will be abiding by our antitrust policy, and this is not intended to promote any specific technology products or services, rather to give a scientific overview of the state of the technology. Agenda, please, Mickey. Today's agenda, we're trying to start things off quickly, get right into the technical content. Dr. Ernest Blatchley, also known as Chip, will take off next, followed by Drs. Karl, Linden, David Sliney, Holger, Claus, and we'll wind up with an overall general question and answer session. Throughout the panel, we'll be taking questions through the Q&A and chat lines on Zoom. They will be collected and we'll respond to them as we can. For those we don't respond to, we will post a Q&A response to our website after the webinar. With that, Chip, if you would, please.
Okay, thank you, Troy. So what I'm going to be doing is providing an overview of the task force in terms of its composition, meaning who was on it, and then provide some definitions that we'll be using in this presentation collectively about what Far Uvc is and the other forms of ultraviolet radiation. And then lastly, just some brief information about Far Uvc sources. So this task force was formed really to address Far Uvc radiation. We are defining Far Uvc radiation as radiation with wavelengths between 200 and 230 nanometers. So it turns out, for various reasons that will be presented in this webinar, radiation in this range has gained a fair amount of attention because it's very effective for disinfection, but less damaging to human tissues, specifically the skin and eyes, than other sources of radiation that have traditionally been used in germicidal applications, specifically with wavelengths between 250 and 280 nanometers. So because of that, Far Uvc offers the potential to fundamentally change how and where UVC radiation is used, and there's the potential for it to be used in occupied spaces. So the objective of this work, meaning the work of the task force, has been to provide an impartial presentation of the available information related to Far Uvc and to provide our analysis of Far Uvc disinfection, safety, and impacts on public health. So the task force itself comprises people from a wide range of backgrounds, including engineering, medicine, consulting, as well as manufacturers of UV equipment and others. So here are the task force members. I've indicated their names in reverse alphabetical order just because there does seem to be a bias to go in regular alphabetical order. And I've also included their affiliations. You'll note also that I've noted the chairs of the various subcommittees that were formed within the task force to address disinfection, safety to human health, and ozone formation. And the chairs of those three subcommittees, Karl, Linden, David Sliney, and Holger, Claus, will be giving summaries of what each of the subcommittees assembled for the white paper. By the way, the white paper is available. The white paper is a document that we assembled to summarize our findings based on that scope that I just described a minute ago. So a couple definitions here. First, this is a general illustration of the UV spectrum, including Far Uvc radiation. So hopefully you can see the cursor. I'm sort of floating around Far Uvc. Again, this falls in the wavelength range between 200 and 230 nanometers. That's as compared to, for example, conventional UV just germicidal irradiation, which falls in the wavelength range 250 to 280. So the wavelength ranges that are illustrated up here come from the International Commission on Illumination. There are similar, though not identical, wavelength ranges that provide definitions of the various forms of UV radiation from other organizations. So what are sort of common far UVC sources? The most common by far is the Krypton chloride Eczema lamp. So I have illustrated in the lower left 2 commercial versions of the Krypton chloride Eczema lamp. It has an output that's dominated or centered at 222 nanometers with a fairly narrow range of wavelengths. There's a secondary output that's centered at about 257 nanometers over here, and optical filtering can be used to eliminate this non-primary emission. So this graph is presented with the vertical axis on a linear scale. Here's the same information on a log scale, just to give you an idea of, first of all, the secondary peak that exists over here and the effects of the filters. The filters are illustrated by the dashed lines, and you can see that the filters do a pretty good job of isolating the 222 output. So there are other sources of far UVC that are out there. For example, medium pressure mercury lamps do emit in the far UVC, but you would need to apply optical filters to isolate that radiation. There are also far UVC LEDs that are available, and here are 2 images that illustrate some characteristics of these far UVC LEDs. One of the problems that exists with these, or among the problems that exist with these, is that they're relatively limited in terms of their output, and they have fairly short lifetimes. So for the time being, they're probably not practical. There are other solid state devices that exist, but for practical purposes, far UVC radiation really focuses on Krypton chloride lamps. So for the rest of what we're going to be presenting here, the information that will be presented will relate directly to those Krypton chloride lamps and their output. Okay, so Troy, I think I'm going to go back to you to introduce the other speakers.
Karl, thank you Chip, thank you very much. This is a great kickoff. We've already started getting several questions, which I believe will be answered during the remainder of the presentations. Next speaker is Dr. Karl Linden on the general disinfection applications. Karl?
Thank you, Troy. Let me get my screen started here. All right. Welcome, everybody. I'll be talking to you today about the work of the Disinfection Subtask Committee. We've been working on gathering data around inactivation of different types of pathogens, specifically looking at respiratory viruses toward far UVC radiation. I'm at the University of Colorado, Boulder, and my contact information is below if you need to get in touch with me. Let's see, go next here. Oops. All right. The overview today will be first talking about how far UVC works. What are the inactivation mechanisms that are present when we have far UVC radiation? Talk about the wavelengths of importance in UVC inactivation and the role of both protein damage and nucleic acid damage. Then we'll talk about how much far UVC is required for inactivation of different types of pathogens, specifically looking at coronaviruses and respiratory viruses and some surrogates. And then focus a bit on the surrogates for UV inactivation of these viruses and how we can use these surrogates in studies for validation, including Phage and other coronaviruses that are not as pathogenic as something like SARS-CoV-2. Then we'll wrap up with some conclusions. So as Chip mentioned, there's a number of UV sources that emit far UVC, and there's a number of UV sources that are what we call conventional UV sources. The conventional UV sources are low pressure mercury vapor lamps as well as medium pressure lamps. And you can see on the left-hand side, the typical output of the low pressure lamp is primarily at 254 nanometers. And the medium pressure lamp has a polychromatic spectral output, which includes the far UVC wavelengths that are important. And some of the early work that went on with virus inactivation, looking at medium pressure compared to low pressure, identified that these lower wavelengths were very important for inactivation of pathogens. On the right-hand side, we can see the Krypton chloride Eczema lamp, and this is the primary output at around 222 nanometers. And as Chip mentioned, also there's a secondary output around 258, but many Krypton chloride lamps are filtered so that we only have emission of the 222 wavelength. So UVC primarily works for inactivation of pathogens by disrupting DNA or RNA replication and degrading proteins. And the wavelengths that are most important here are those in the Far Uvc and the UV germicidal range. And that's between 200 and 280 nanometers. These are the primary wavelengths that we're working with as engineers to try to design UV systems that are effective for disinfection. And UV is very effective for inactivating all types of organisms, whether it's bacteria, viruses, protozoa, any organism that is based on a nucleic acid, DNA and RNA, which are all of them, can be affected by UV. The primary mechanism for inactivation is conventionally known as kind of producing things like thymine dimers and disrupting the nucleic acid bonding. And you can see the small photo on the left-hand side about looking at the double helix and seeing how an incoming photon gets absorbed by the bases, and those bases get torn apart at the hydrogen bonds and form double bonds on adjacent pyrimidine bases, and that causes an activation of the pathogens. Looking a little more closely at that, the first law of photochemistry states that only radiation that is absorbed can produce any kind of photochemical effect. And if you look at the graph on the right-hand side, we see the absorbance of both DNA and nucleic acid here and proteins. And this is looking at wavelengths between about 220 up to 300 nanometers here. And this is absorbance on a log scale. So what we see first is that for genomic damage, for DNA and RNA, which interferes with replication, the primary absorbance for the nucleic acids are around 260 to 280 nanometers, as well as below 220 nanometers. So we expect those mechanisms to be quite dominant for inactivation, given the damage that occurs to the genome and the nucleic acids. But proteins also are very important for viruses specifically. And if we can think about damaging the proteins on viruses, we can enhance inactivation of those pathogens. If you look at the two pictures on the left here in the bottom, we see SARS-CoV-2 and adenoviruses. And all these little features on the outside of the virus are all proteins. And these proteins mediate the attachment mechanisms and the infection mechanisms of the viruses. If we could damage those proteins, we can cause an activation of these pathogens and eliminate their infectious capability. And the proteins primarily absorb in the range of, say, 280 nanometers here in this little peak here, as well as very strongly below 240 nanometers. You can see this a little bit more closely in this graph here, which reproduces protein absorbance and nucleic acid absorbance. The nucleic acids in the black down at the bottom and the proteins in the red here. And this is absorbance on scale on the y-axis, again, 200 nanometers up to 300 nanometers. And what we can see here is down at 220, the proteins absorb much more strongly compared to 254 absorbance. This is all normalized to the absorbance at 254. So we see the proteins are absorbing very strongly at 222 compared to nucleic acids. And this we hypothesize is one of the main mechanisms for why UV 222 and Far Uvc is so effective for inactivation. So we collected data from the literature. We looked at all data for appropriate methods as well as the quality of the data. We looked primarily at peer-reviewed publications and pre-publications that were in peer review. We included experimental data as well as model data, which we'll show you. The data are from studies across UVC wavelengths. We considered all types of data. We looked at both 254 nanometers as well as 222. We entered those data into a shared spreadsheet and shared all the publications in a folder with the UVC task force. And everyone on the task force reviewed those data. We plotted them and analyzed them, and we drew some conclusions, which I'll talk to you about now. So I'll show you a number of plots that look like this. This first set of plots is explaining the UV inactivation of some common respiratory viruses. And on the left, we'll focus here first. This is for 254 nanometer UV inactivation. The y-axis here is a log scale for the ratio of the number of survivors to the number of viruses inactivated. And this is typically how we show inactivation data on a log scale. On the y-axis here, we have UV dose or UV fluence that's used. And you can see here in the box all the studies that were used. And you see most of these studies we're looking at were from 2020 and 2021 as the interest in respiratory viruses and inactivation of aerosols became more and more of interest due to the COVID-19 pandemic. On the right-hand side, we have 222 nanometer inactivation. And again, we have the UV dose on the x-axis and the log inactivation on the y-axis, where each of these major ticks is 1 log reduction. So first we'll look at 3 log inactivation and what UV fluents or UV doses are required for that. 3 log inactivation equivalents to 99.9% reduction in the infectivity of these viruses. And what we see here first is that to achieve a 3 log reduction, we need a UV dose of about 5 millijoules per square centimeter, UV fluents of 5 millijoules per square centimeter. And these data are from the data we took from the literature. And there's a number of data that were also modeled using genomic-based models that showed very similar inactivation efficiencies. Approximately about 6 to 7 millijoules per centimeter squared were required for 3 log inactivation based on all the model data that were out there. So these are very, very low doses for inactivation. It's very easy to inactivate these respiratory viruses. And we're talking about the SARS-CoV-2 virus here. We're talking about human coronaviruses that cause colds. We're talking about murine hepatitis virus, which is another type of coronavirus, as well as influenza viruses here. If you look at 222 for 3 log inactivation, we see a very similar reduction capability. We have about 3 log reduction at a dose of less than 5 millijoules per square centimeter. So UV222 is very effective for inactivation, as is UV254. We see very high levels of inactivation at very low fluence levels. And typically for UV applications, we try to give a UV fluence of between 20 to 40 millijoules per centimeter squared in various applications such as air handling systems and water disinfection systems. So these doses are very, very low compared to what's typically applied. Let's look at inactivation of some common respiratory viruses now on surfaces and aerosols. The previous data I showed you was in aqueous data because it's quite a bit easier to do this work in aqueous data and very thin film aqueous solutions, but we want to also know how does it work on surfaces and aerosols. In this case, the data are quite limited, but what I'll show you here is, again, UV dose on the x-axis and the log reduction on the y-axis. And you'll see these open symbols here. This means that the data were greater than these numbers. We don't have the actual number, but we know it was at least this amount. So all these open symbols indicate that we don't have precise data, but we know the data is at least as high in activation as is shown here. So here we have also SARS-CoV-2, we have human coronaviruses and influenza viruses as well. And again, for about 3 log reduction, we see a UV fluence of less than 5 millijoules is required for inactivation, which is very similar to what we saw in the thin film aqueous solutions. Now, I want to point out that the UV inactivation on surfaces, this data is quite limited at this point, and we need to develop more data to help support these types of inactivation relationships. And we know that inactivation on surfaces is also affected by the type of surface, the reflectance of that surface, the state of the virus, and also the media surrounding that virus. For instance, is it surrounded in saliva or dried up on some other media that's causing interferences with the transmission of UV to that virus. And as far as aerosols go, UV inactivation in aerosols is very effective and as effective as aqueous media, but there are also limited data on viruses specifically, but there's a rich data set out there for other types of microorganisms. And we know that UV works for organisms embedded in aerosols, but we also have to consider things like relative humidity, temperature, and absorbance of the aqueous layer that surrounds those pathogens. So it's a bit more complex thinking about inactivation of aerosols and activation of viruses on surfaces. But the data look very, very promising. Now we'll look at some inactivation of coronaviruses compared to Phage. And Phage are surrogates that are used for viruses. They're much easier to grow, easier to use in typical labs, and don't require high levels of biosafety. So we consider these as viral surrogates, and these are also these studies were also done in the aqueous phase. On the left-hand side, again, I have 254 UV inactivation, and then on the right-hand side at 222 nanometers, the Far Uvc. So we're comparing the two. And here in blue, we have most of the pathogens here, and here in red and to the right, we have most of the Phage in this inactivation data set. So let's look at, again, these data for 3 log reduction. What we have here is similar data. This is the same data set we showed before, less than 5 millijoules, around 6 millijoules or so for 3 log inactivation. And for the Phage surrogates, we have similar inactivation, about 15 millijoules for 3 log. So what we're trying to do here is see, can these Phage represent and conservatively represent inactivation of respiratory viruses. And what we see here is they definitely can. These phage are easy to propagate. They're easy to use. They're very similar in some cases to the viruses of concern. And the inactivation is a little bit more difficult with these phage, which makes it a good surrogate because it's going to be conservative for that. And we see some of the other phage, such as Q beta phage, even require higher doses, around 30 to 35 millijoules for 3-log inactivation. So phage like T1 phage seem to be very, very good as surrogates, and Q beta could be a very, very conservative surrogate. This is at 254, and similar data for 222, looking at about 5 millijoules for 3-log of these respiratory viruses, the coronaviruses, and we see for the T1 phage affluence of about 12 millijoules for about 3-log. So these represent some good surrogates that we can use, whether it's T1 phage or this Q beta, or we also have Phe6 is another phage that can be used. And these phage can be very similar also in the genomic makeup to the coronaviruses and to respiratory viruses. But it's good to see that the behavior is quite similar, and these phage can be used as surrogates in studies to prove that you're delivering enough fluents that can also inactivate viral pathogens such as these respiratory viruses. And lastly, just comparing coronaviruses specifically just to the surrogates, looking at SARS-CoV-2 as well as murine hepatitis virus, we see that the UV222 fluents, again, is very low inactivation levels, very low doses for high levels of inactivation for 3-log, less than 5 millijoules for these coronaviruses here. And these phage surrogates can be used to represent these surrogates. I want to point out that the T1 UV phage, that's quite a good surrogate as far as the fluence goes, very similar fluence required for the same levels of inactivation, is a double-stranded DNA phage, and it's non-enveloped. The coronaviruses are enveloped, and they're typically RNA-based phages, RNA-based viruses. Q beta, on the other hand, is a single-stranded RNA phage that's non-enveloped, and Phe6 is a double-stranded RNA phage that's an enveloped phage. So we look at a variety of types of surrogates that we can use for representing inactivation. And when we think about 4-log inactivation of these viruses, we're thinking about doses between about 5 to 10 millijoules that are going to be effective for 99.99% inactivation of coronaviruses. So wrapping up with the conclusions, we definitely feel that the efficacy of Far Uvc against viral pathogens is at least as high as that of conventional UV germicidal radiation, the 254 nanometers. And there's a long history of UV technology being used as a disinfectant in a wide range of settings. And the general conclusions here are that UV radiation is highly effective for pathogen inactivation, especially for respiratory viruses, which require a much lower dose than most pathogens that are known. Coronaviruses such as SARS-CoV-2 require very low UV fluence, and UV22 is definitely effective and as effective as conventional UV application. The second conclusion is that inactivation of viruses and other pathogens by UV is effective on surfaces and aerosols as well. Of course, there's some caveats here. Coronaviruses, including SARS-CoV-2, have been effectively inactivated on aerosols and surfaces, and there's been a number of publications to this effect, which is very encouraging, but the data are limited for a diversity of surfaces and in aerosols, although data for other pathogens do exist, and these data are also being generated for coronaviruses. Then absorbance by the matrix needs to be considered for aerosol inactivation and inactivation on surfaces, because that may diminish the effectiveness of the UV. So this is an area of research that is still in need. The last conclusion is that there are numerous pathogen surrogates, such as phages, that are non-pathogenic, that are known that may enable validation test methodologies to be pursued. And use of these phage can be very effective for demonstrating effectiveness of UV sources. So the other coronaviruses, for instance, can be also thought of as surrogates. These are non-pathogenic or less pathogenic than something like SARS-CoV-2. These are definitely excellent surrogates. They have very high similarity as far as genomic similarity to SARS-CoV-2. There's also numerous phage that have similar inactivation kinetics, which I've shown you, the T1 phage, the Q beta phage, and these surrogates can be selected, but the selection of those should depend on the target virus and the wavelengths of UV used. With that, I just want to refer you again to the white paper that was just published, and all the references that these data came from are encompassed in that white paper. And thanks a lot for your attention. I'm happy to take some questions or during the panel.
Very good, Karl. Thank you so much. We've gotten several questions. let me address a quick one or bring up a quick one, and I'm not sure if you or Chip would be best to respond. What kind of filters for Far UVC have the least blue spectral shift?
That's a great question. I think maybe that may be something we can punt to the panel when we have a bunch of the manufacturer representatives on board. So maybe we can punt that.
That's fine. We'll put that on the parking lot for the Q&A session at the end. The next one asks questions about what studies have been done for the inactivation of aerosols using Far UVC.
Yeah, there's definitely not many studies, but there are a number of really strong studies that are out there that definitely illustrate and demonstrate clearly the high levels of inactivation you can achieve. We need to do more studies that are in different types of matrices. For instance, in human saliva matrices, that's one area that needs to get looked at more closely. But we know that UV works. We know it works against aerosols and different types of pathogens. Some of the work that it's been done, we cite in the white paper. So I want to point you to that and look at those papers specifically because all the details are in there. And perhaps Dr. Brenner, who's on the panel, also can discuss some of the studies he's worked with Far UVC on aerosols specifically, because some of that work comes out of his lab.
Very good. And I believe one or more of our panelists are typing in additional answers as well. Next question is the liquid layer found in an aerosol droplet. Won't this reduce the efficacy of Far UVC?
That's a great question. The importance of absorbance is a factor for sure you need to take into consideration with UV. I mean, that's going to be the main driver for the penetration of the photons. But when you think about how thick the layer is, that's another very, very important factor. If the layer of aerosol around the pathogen is very, very small, for instance, on the order of microns in size, in depth, then there's going to be, of course, the aerosol, sorry, the layer of liquid will have some absorbance to it, but that absorbance effect on the ability of the pathogens to penetrate will be quite minor if it's a very, very thin layer. If it's quite a thick layer, if we're talking about, millimeters of depth, then we see certainly blocking of UV photons getting into the heart of that aerosol and activating the pathogen. So that's something we need to look at maybe a little bit more closely with some modeling. But what we know of right now is that the thin layer that occurs around pathogens in an aerosol is so thin that it doesn't block the photons appreciably. That needs to be looked at a little bit more in different types of matrices, but there's those two factors. It's the absorbance of the layer as well as the depth of that layer, and the penetration of the photons will be affected by those two factors.
Very good, thank you. We have a couple of more questions which are actually going to be answered in Dr. Sliney's presentation next on the comparative benefits between 222 versus 254 and the OSHA 8-hour exposure limit. We'll save those questions for the next presentation. Couple of more questions here. What's the best way to get more data on phage viral surrogates?
Thankfully, there's a lot of data that abound for phage viral surrogates. So there's lots of data that we cite in the white paper, and I'm happy to provide more data as well. There's been a number of great studies that look at UV inactivation across UV spectral ranges for different types of phage. So that data is out there. More of that data is being developed as well for surfaces and aerosols. So we'll see that data set become quite rich, and all those data are in our publication. And I'll be happy to share additional data sets with folks of interest. Just get in contact with me.
Sounds good. A follow-on question: with much smaller genomes, why are phage more resistant to UV damage than larger genomes of human viruses?
Well, that's a good question. Larger genome organisms tend to be more susceptible to UV. I think of it as more like target theory. There's more target nucleic acids available for the photons to damage, to cause inactivation. If you have a very large genome, it might be more likely that the damage will occur due to the photon being absorbed by that genome versus a very, very small genome that might be harder to, if you want to call it, hit with a photon. So that's one theory there. And the other theory is the actual genomic makeup and the number of bases in the RNA, along the RNA, that are adjacent to each other that can actually cause typical types of damage. For instance, the pyrimidine bases, when you have adjacent bases, the damage from UV is more likely to form dimers across those pyrimidine bases if you have more that are closer together. So the genomic modeling is really, really fascinating, and a lot of advances have been made in this modeling. And we've cited some of that in our paper, but mostly for 254. We need to do that modeling now for 222, but we think it's going to be very, very similar as far as what the outcomes. But it's very interesting to know that the genomic makeup, the bases and the location of those bases on the nucleic acid, along the RNA or DNA, would be very important as far as the likelihood of those that damage to occur and the inactivation to be effective.
Okay, very good. We've got several more questions which we'll keep on the list for the Q&A session at the end. It is time to turn it over to Dr. Dave Sliney to talk on the safety aspects of 222. David? You're on mute, David.
There. Sorry about that. I hope this is it full screen, or do I need to make another adjustment?
You need to go to slide presentation mode.
Okie doke. Let's see if this works. I hope that shows it all right. Is that right?
Mickey, there, we're good.
Okay. I just want to point out that a major consideration in the application of germicidal UVC of any wavelength has to do with safety. And there are two types of accidental overexposures that can occur. Traditionally, these occurred by maintenance workers or by poor installation of equipment. But the effect on the eye is what most people remember, and that is what we call photokeratitis or photokeratoconjunctivitis, to be even more elegant. And this is also known as welder's flash or snow blindness. It's the same effect from ultraviolet irritation of the outermost layer of the eye, which is the cornea. That's the most sensitive tissue. It's also possible to get a mild sunburn or reddening of the skin, erythema, but it will never be as severe as a true sunburn, which is caused by the UVB band, which is more penetrating. So the delayed effects of UVC are pale in comparison to UVB or sunlight. And the reason is that the UVB, although less energetic photons, penetrate very deeply to the basal layer of the epidermis, the germinative layer, and that's considered necessary in order to promote skin cancer. Whereas UVC is heavily absorbed in the most superficial part of the epidermis and stratum corneum, which is above the germinative layer of the skin. And in general, the reason that Far Uvc is considered particularly attractive from a safety standpoint is that essentially all proteins, as pointed out before, heavily absorb energy at shorter wavelengths. So the penetration depth in skin and eye tissues becomes very minimal. Let's see. Just to emphasize this, the 200 nanometer wavelength is completely absorbed by the stratum corneum, which is the outermost layer, a thin layer of skin that's actually dead tissue. And 222 barely penetrates it. And 254 nanometers from the mercury lamp gets well into the epidermis, but only a very, very small fraction can actually reach the basal layer of the epidermis. Then as we move over to 300 nanometers, which is the center of the UVB, it does penetrate to the basal layer. And on the right-hand side is the action spectrum that's standardized by the International Commission on Illumination, or the CIE, and the ISO. And you can see on this linear graph that the strong efficacy is around 300 nanometers. And it's very much limited in terms of the greatest risk to the UVB. It always surprises biologists when they first learn that the much more energetic photons of UVC pose less of a safety hazard. And the reason is because we have very good shielding in the outermost tissues. Now, this is a bit complex, but I just want to point out that there have been some very good quantitative studies of this whole issue of skin cancer and risk from UV. And we see in the far left panel the studies performed by Bruls in Utrecht in the Netherlands several decades ago that show very clearly that as you get into the UVC, very little gets through to the most superficial cells of the epidermis that are soon going to die and become part of the stratum corneum, and less than 0.1% is reaching the basal layer. So by comparison to 300 nanometers, you see that something like 20% reaches the basal layer. The middle graph is what we call the action spectrum, the relative risk for different wavelengths of eliciting any response. In the UVC, this is a photokeratitis, and that's the bold line. And then you'll notice that the skin action spectrum, which is the dashed line for erythema or sunburn, is sort of plateaued between 250 and 300 nanometers. It's not given for shorter wavelengths because for most sources, people are not concerned about wavelengths below that. And the dotted line, which goes down nearly to 10 to the minus 3 or 0.1% efficacy, is the action spectrum for non-melanoma skin cancer. The spectrum on the right is the solar spectrum on Earth. And as you could see, the UVC is well blocked by the ozone layer in the stratosphere, and only trace amounts of UVB reach the Earth, but that's what is our only real known risk for skin cancers by optical radiation. Some people ask questions of whether they're particularly sensitive individuals, because this is a well-known concern when we're dealing with longer wavelength ultraviolet lamps, and this is often referred to as photosensitivity. And this is an effect where longer wavelength UV, the UVA band, the type that's used in fluorescence testing and novelty devices, that energy can be more damaging to skin if there's a photosensitizing chemical in the skin, or if someone's taking a photosensitive type drug such as tetracycline. And so occasionally we have people who are taking a medication and they suddenly get a sunburn from a near UV source. But this is not an issue with UVC because the energy doesn't penetrate into the epidermis deeply enough to cause much of an effect. The thresholds for exposure for erythema or sunburn vary a great deal with skin type. There's different skin types depending upon how much melanin pigmentation you have, darker skins being rather insensitive and very pale white skins being quite at risk, particularly people of Celtic origin, such as myself, who freckled when I was a child, have a very high risk, and I've always had to avoid sunlight exposure. The point is, though, that the takeaway for this panel is that UVC wavelengths penetrate so little that it's highly unlikely that we could detect some individuals that would have much more sensitive. We still don't know about individual variations with the eye sensitivity because most of the energy is absorbed by the tear layer. And it may be that some people with thinner tear layer may see an effect at a lower dose than others. So switching then to the eye, the UVB penetrates into the cornea, and some of the longer wavelengths of the UVB actually can penetrate to the lens. The UVC, though, is totally blocked by the cornea, so that the only tissue at potential risk is the cornea. And as you can see on the left, 222 nanometer radiant energy is largely absorbed in the tear layer and reaches into the epithelium. The 254 nanometer mercury line gets a little bit deeper into the stroma, and then 270 a bit deeper than that. On the right panel, we simply show longer wavelengths of ultraviolet, and I just wanted to point out that near ultraviolet just produces lens fluorescence because it does penetrate to the lens, and most of the energy is blocked by the crystalline lens, which gives further protection to deeper tissues such as the retina. We have exposure limits that have been developed over the last decades and have been largely unchanged since 1985. There's several groups that have proposed these, and they're basically identical. They are identical in the ultraviolet C. That's the International Commission on Non-Ionizing Radiation Protection, or ICNIRP, and the American Conference of Governmental Industrial Hygienists, ACGIH, which also has basically the same limits and actually preceded the ICNIRP proposals by a decade. And the safety limits depend very much on wavelength, and we can see in the right-hand panel thresholds for minimal effects, for example, on the cornea, and there's data for human and a number of different animal species as a function of wavelength. And you can see that the wavelengths down around 220 shoot up quite a bit. There have been some more recent studies which show that by using much narrower band wavelengths that the thresholds are still higher. And you'll notice that the most sensitive wavelength is down around 270 nanometers, where the safety limit is 3 millijoules per square centimeter. So when we have multiple wavelengths, we perform a calculation known as spectral weighting of the emission spectrum of the lamp, and the basic effective irradiance must be below the 3 millijoules per square centimeter over the entire exposure duration, which is normally considered 8 hours or less. There's another criteria that is largely responsible or largely applicable just in the UVA, and I won't mention that. So as an example, at 254 nanometers, the limit is 0.2 microwatts per square centimeter for an 8-hour exposure, or 6 millijoules per square centimeter. For 222 nanometers, it's higher. It's up at 23 millijoules per square centimeter, so several times higher. And we see this mathematical expression for those of you who like to see things mathematically, which is the spectral weighting formulation that we use to calculate the effective irradiance or effective radiant exposure. And we see over here that the, again, the same action spectrum that I had shown before. The key point is that there's a large safety margin for human skin exposure in the UVC. And it's been proposed to, now that there's a great deal of interest in germicidal UV again, to have a separate limit that's much higher for the skin. And the proposals put out by ACGH just this year in their threshold limit values book is shown here for the skin and the eyes in both formats. The left-hand panel is the exposure limits, as you can see on the left-hand ordinate. And on the right hand, we have the same proposal prepared as action spectrum. And so as you can see, the proposed guidance for the skin is the green line. And you can see that that's quite a bit larger than for this proposed levels for the eye, which is the red limit. And then you'll notice that the black line is the current official limits of ICNIRP and ACGH. So if these are accepted, you see at 222, there's quite a large change by an order of magnitude or more in terms of comparison with the current limits. The last thing I want to mention when we're talking about safety is how we apply the limits. And there's a number of cases where people go to the extreme simplicity of assuming that people are exposed to what they might measure right in front of the lamp for a whole day, for 8 hours or more. And you can come up with very appearance of a very unsafe condition, when in reality, people are not exposed as a rule continuously. And this is just a simplistic plot to show you that, for example, if we had a 222 nanometer lamp, we could have quite a bit higher values than the average irradiance, which is down here in the light shaded blue. 30,000 seconds is 8-hour exposure. There's a difference of opinion as to whether that should only be applied to 8 hours or what happens if you're under the source for 15 hours. And there's enough evidence in the clinical literature to show that you lose most of the additivity after a few hours. So probably if you just apply the 8-hour limit here for even longer times, it's not going to be a problem. And people always tend to overestimate what they're really exposed to. And here we've got a good example of an actual approach towards assessing risk and permissible exposures in some real installations with some downward directed lamps as are proposed for 222 nanometers. And for the eye, it's important to recognize that people look directly at the source very rarely. They're normally looking forward or slightly downward, and the upper lid completely blocks the overhead light. And for those of us in the lighting community, we're very familiar with the glare index and the fact that you don't really see above you if you have some glaring downlighting, and it's always above 45-degree angle. You don't have to worry about the complaints of glare. So proper application of the standard would help a lot. And unfortunately, there's some efforts to try to come up with standardized methods to do a safety assessment that don't consider these practical approaches. And hopefully that will be corrected with the publication that's expected in the next month or two by the Illuminating Engineering Society, recommended practice for use of germicidal radiation. And I'll end simply by saying there are lots of references here, but I put them on here simply so that we can refer to them later. Thank you.
Very good, David. We only have time for a very few number of questions, but one question that keeps coming up refers to IEC standard 62471. And how do we, is there a way to certify whether or not UVC devices in general, 222 nanometer devices specifically, can be tested against 62471. Can you address that?
Well, that's a manufacturer standard, and that's designed to provide risk groups of a lamp. And the risk groups then should be taken into account when people are actually assessing the risk in the real world situation. So this provides a terrible challenge for, say, a test house to try to say, well, it's going to be, for example, a typical UV fixture of today of 254 is going to be a risk group 3, or which is a high risk, or it's not even effective. So the problem has been, how do you set up a sort of worst case exposure condition, for example, for overhead lamps or downward lamps, and where do you make the measurements? And the 62471 does talk about properly using time-weighted averaging, and it also talks about using a 80-degree cone, both of which are very important. And if you don't take those into account, you're going to have a gross overestimation of the risk.
Okay.
It's a challenge. Thanks.
One last question, David, and I'm pulling together several questions about conditions which might increase sensitivity to 222, such as pregnancy, changing hormone levels, having had LASIK surgery, any other IOLs that might have been conducted for people. Can you address?
Compared to a lot of risks from chemicals and physical agents, there's just very little evidence that we would be concerned about anything such as pregnancy or any particular skin condition, simply because the energy doesn't penetrate the body. But on the other hand, I can't completely rule out that immediately after LASIK surgery that you wouldn't have a greater sensitivity. But once, a normal healing process for the cornea has taken place, I wouldn't think that there'd be any increased sensitivity.
Very good. Thank you, David. Good stuff. All right, time to move on. We've had several questions about ozone, and our expert is Holger Claus. Please, Holger. You're on mute, Holger. Mickey, can you take Holger off mute?
Yeah, I've asked to unmute. I've sent a note to ask to unmute.
I can see him trying to do it, and he's obviously having problems.
I am very sorry. Can you hear me now?
Yes, sir. Thank you very much, Holger.
When you
The
work
floor
with-
is yours.
When you work with too many screens, I am sorry. So you can see my screen. The UV task force also looked into another risk associated with Far Uvc lamps, which are Krypton chloride lamps, and that is the generation of ozone by these lamps. The risk is different than normal GUV lamps, mercury-based lamps, because mercury-based lamps, you can make them basically ozone-free by choosing glass. With Krypton chloride lamps, you don't have that option, so these lamps definitely do create ozone. What is ozone? It's basically an unstable gas, oxygen, and it has a third atom attached to it, so it's unstable and highly reactive, oxidizing, and it's very heavily regulated, but it's also widely used in water disinfection in the food industry. The good thing is normal people can smell ozone at very low concentrations of about 30 ppb. And the limits, the threshold limits that are being set, at least in the United States, are down to 50 ppb or 0.05 ppm, depending on exposure time and so on. They can be slightly higher. I assume that these values are not much different around the world. So we talk about 50 ppb as a maximum exposure. How is ozone generated in lamps, by lamps? There's essentially two ways, either by radiation, UV wavelengths, and electrical discharges. And I want to make it clear upfront, we are talking about the ozone generated by a lamp. We will get into that later, but this is not necessarily what is being emitted into a room. So ozone generation by radiation. Since the ozone layer is a very, very important part of our atmosphere that has been researched and understood for a long, long time, it is very much related to the absorption of the oxygen to UV photons. And this graph here shows the absorption of oxygen. And you can see this is logarithmic absorption, and it drops off very steeply in the so-called vacuum UV range below 200 nanometer, but there is still some absorption at 222 nanometer left. But in practical terms, for the lamps, it is more important that Krypton chloride lamps have a little bit of a peak below 200 nanometer. And since the absorption is basically exponentially dependent, this little peak has a much higher impact on ozone generation by radiation than the 222. More important in practical purposes seems to be the ozone generation by discharge. These lamps are eczema lamps. That means there's no electrodes inside, and the lamps are driven by very high voltages, typically somewhere between 2 kilovolt and 10 kilovolt, which are basically applied to the outside of a glass bulb. And then it depends how the lamp is built, how big is the voltage, what is the power. Little discharges can form on the outside of the lamp, so-called corona discharges. And these discharges create a lot of ozone in air. And that amount is usually much, much higher than whatever is being created by radiation. And since it is a discharge, it depends on the parameters, especially the driving voltage and of course the lamp power. That being said, the ozone generation will depend on the lamp design and the lamp power. But there's ways to reduce the ozone. In applications, always remember the ozone generated by a lamp is not necessarily the ozone emitted into a room. You can block the ozone. You can modify fixture design. Just by enclosing the lamp, the ozone will be trapped, most of the ozone at least. If necessary, you can put ozone destruction filters into the fixture. In fixtures, you can also just add a quartz window that will block some of the ozone or most of the ozone from coming out. In practical applications, ozone naturally decays, but fairly slowly. But one thing to remember, ozone is very highly reactive. So many organic materials react very quickly with ozone, especially nylon and rubber materials. And of course, that will eat up ozone. Overall, the easiest way to lower ozone concentrations is, of course, ventilation, air exchange, and that is the most efficient and easiest way. Nonetheless, the goal should be to create the least amount of ozone in a room. The ozone concentration can be calculated. You can look into our paper for more details. And an important measurement is the ozone generation rate of a lamp. Now, I want to say that this ozone generation rate, of course, only takes the generation into account. In practical environments, you will have ozone destruction and other effects. So when you calculate ozone concentrations with this formula, you can expect that in practical measurements, it will always be less. And of course, the formula assumes that the air is perfectly mixed, which may not be true. Nonetheless, it is a good way to at least make some estimates for the expected concentration in rooms. Now, how do you measure the ozone generation rate? For really strong ozone generating lamps like mercury lamps or xenon eczema lamps, they are typically put into a tube. You flush some air or oxygen over it and measure the ozone concentration at the output. Now, these lamps, these Krypton chloride lamps, at least the modern ones, are not necessarily tubes, and they are also creating such a small amount of ozone that it becomes very challenging. So in the task force, we investigated different methods how the ozone can be measured. We came up with a relatively quick and simple way. If you enclose such a lamp into an enclosed volume, small one, like shown here, 35 liters about, made from a material that does not react with ozone. You turn on the lamp and you measure the ozone concentration over time. And the gradient of this ozone generation, basically ozone concentration, basically shows you, gives you the ozone generation rate. We compared a few data that we could get from various lamp manufacturers of various lamps. And as you can see, the values vary quite a bit. So, So one lamp created 85 micrograms per hour, which is a very small value. Another one, 12 micrograms. And then we get into different kind of lamps, what I mentioned before, the cylindrical lamps. So a 75 watt lamp creating 12 milligrams per hour. Another lamp which is much higher wattage, but is built differently than that 75 watt lamp, only gives 1.3 milligrams. So just to emphasize, the ozone generation will depend on the lamp design and the power. So in the United States, there is a UL 867 that is being applied for air cleaners and is measuring the ozone concentration. That is based on a sample room of 1,000 cubic feet, almost 30 cubic meter. And we can basically do some calculations for these lamps that I showed before and estimate how much concentration will this lamp create. Remember, in practical application, 0.05 ppm. This UL 867 standard basically sets the limit at 50 ppm. So if we take these two low power lamps, you see that the concentrations would be far below the limits of 50 ppb. But these higher power lamps can very much exceed these limits. But it has to be considered, so this assumes 24-hour on. In practical application, especially if you work with ACG/IH limits, the on time of these lamps will be much, much lower. Yeah, you see, it's basically with these low power lamps, 0. With the 300 watt lamp, you may get close to the limits. But I mentioned before, the data in real measurements will be much lower. For instance, with lamp B, there have been actual measurements under UL 867, and the measurement results were essentially 0 or at the measurement resolution and limit. And also we have one other data point. If you take lamp A and put just a quartz window in front of the lamp, the ozone generation drops by 2/3 very quick. So there is simple ways to lower the ozone emittance into a room, but these data also show you must do your homework. You must go at least to your lamp supplier and get the data so that you can do your estimates. And at the end, you will have to do ozone testing anyway, especially if you want to sell in the state of California, because there it has basically become mandatory. Far Uvc fixtures are considered air cleaners and must be certified under UL 867 for ozone generation. And I am not familiar enough with international regulations, but I assume it is not much different. When you go into testing, always keep in mind you are not testing the lamp or not even the fixture and always on time. If you apply a fixture, you want to run it with the actual on time of the lamp. That is likely much, much shorter than 8 hours, and you will run it with ACG/IH limit, so it may only be on for half an hour in 8 hours or something like that. And the ozone generation will be even lower. At the moment, unfortunately, there's no way to get around it, even if every manufacturer tests the same exact lamp and the same design, you still have to get your own data. Yeah, I mentioned, yeah, you should in your fixture designs, you should decrease the ozone emission to the minimum. Ozone is a dangerous gas, and we should limit the exposure to people to an absolute minimum. And that is it from my side. Thank you very much.
Hey, Troy, you're on mute.
Thank you, Mickey. I found my unmute button. Holger, good presentation. Thank you, sir. We've been getting lots of questions. I'm going to combine several into one, and that is questions about 222 nanometers itself. How much ozone does it generate compared to 207 and below? And I think you addressed it, but please again.
At the moment, I am not aware of one paper or measurement that measured only the 222 influence on ozone generation. It's at the moment we can basically attribute all the ozone that we measure to the two factors that I already mentioned. And especially when we talk about low power lamps, it basically should not be a concern.
Okay, so as long as we've got the corona controlled and we've got it filtered, so we don't get into the shorter wavelengths.
And we block the lamp from the outside with a glass window, so that any ozone that is generated will not come to the outside into the room. I think we have already a good product.
Very good. Thank you, sir. I'm looking back over the questions now and looking at the time. I think it would be good to go ahead and go into general discussion, if all would agree. And we'll start going down some of the general questions, and we're still getting questions on I'm trying to pick out the best one. A question about 222.
Sorry, if I could pull a question. Yes.
Please, Rich.
It would, I think David Sliney can possibly answer this best. It's relating to essentially dose reciprocity, and the question is about whether the radius or the intensity of the exposure has an impact in the risk, or whether that it's all about the total exposure. And I think that's also possibly, are we talking on seconds, minutes, hours, or days here? I think, David, you have a good perspective there.
Right. This can be a little complicated, but basically reciprocity, or the Bunsen-Roscoe law of photochemistry, applies as long as you don't have repair processes or cells disappearing or something like this. So what it effectively means in studies, for example, of erythema and photokeratitis in the laboratory under controlled conditions, you see reciprocity pretty good up to about 4 or 5 hours. And then it takes a little bit more energy and a little bit more energy and so on. And it's very difficult to quantify that exactly. Ironically, one of the best studies done ever on this subject was performed in 1928 or so by Hauser in Munich. and I'm not sure that anyone has done a really careful study since then, but that basically shows that there's a slight additivity over a few days. And in deriving the exposure guidelines, the assumption is that normally you're going to sleep overnight, and there's a lot of cellular repair that goes on at that time, or sloughing off of tissues. The corneal epithelium that gets injured in photokeratitis, those cells slough off. The normal lifetime for those surface cells is only 48 hours anyway. So any damage is going to be to disappear within a couple of days from UVC photokeratitis. As for the skin, I think there's enough of a safety factor, safety margin in most cases that we don't really have to worry about significant additivity, certainly in the ultraviolet C. And that's probably true even for the proposed revised limits for the skin. But I noticed on the list of questions that Ed Nardell asked about 24 hours, and that's so difficult to answer because that's the question you always get in an ICU where a patient is being is bedridden and perhaps their face is facing upwards. But I talked to some ICU nurses and they sort of laughed and said, well, you know, if the lids remain open very long, we close them in a patient, for example, who's comatose. So that probably there's little or no significant additivity spread over 24 hours. But normally in this situation, you're worried about people who are standing. So the limits that are down at the patient level are quite a bit lower. And there was a study done at Harvard Medical School some years ago, about 20 years ago, that quantified what types of exposures occurred at different positions in a hospital and showed that much lower levels are going to occur down at the bed level to begin with. I hope that answers.
Okay. Couple of questions, David, for you as well have come up about when do you think the new exposure guidelines are going to be enacted?
Well, ICNIRP, the International Commission, has not even started deliberations, as far as I know, on this subject, but the ACGH proposed this only this year, and the normal process for what they call notice of intent to change is that after 1 year, they review all the comments received and review the situation. And perhaps if there are no problems or challenges that come up, the earliest that in the ACGH process that new limits could be published would be next year in January. So it's a little hard to say. There might be some little minor modifications. I really honestly don't know. It's hard to predict. It could be next year, it could be another year after that.
Here's a general question. Do LEDs exist for far UV frequency wavelengths, 222 nanometers plus or minus? Who'd like to address that? Rich, how about
Yes.
you?
Yeah, I can give part of the answer for sure. Yes, they do, but not in the way that conventional UVGI LEDs, UVC LEDs would in the 250, 200, 80 nanometer range. There's, I believe, one commercial manufacturer. I'm not sure whether there's current availability for those devices. They do exist in laboratories. This would be, for those who have experience with the UV industry, very similar to, in my perspective, the UVC LED state 10 to 15 years prior. You can get hold of the devices. They are being actively researched, and it's in the academic literature. But this is much more towards the development of the semiconductor technology than upscaling for mass manufacture. So they do exist. There are research groups actively pursuing developments. They are currently not at the output powers that are required for disinfection applications. Current uses are more towards sensing or early adopters. If anyone is interested in building a Far Uvc LED system, now's a great time to get into it. Recommend getting a hold of technology if you can, and you're really learning to understand and apply it. But that's for those thinking this is a UVC LED solution to the pandemic. They will not come in time. Be prepared for the advancement of the technology. It will come. There are challenges, but they're being met with a lot of funding and a lot of research. Far UVC LEDs will exist in coming years, but as a practical application for disinfection, not today.
Very good. Thank you, Rich. Thank you very much. I'm going to queue up Dr. David Brenner for a question here, especially given the depth of animal studies that you have done. A question has come up: is 222 as safe for pets as it is for humans?
Well, that is a good question, and it depends on the thickness of the stratum corneum for the pets. But unless the pet is a hairless pet, the skin is going to be protected by the fur. In terms of eyes, it does appear that the tear layer is relatively similar and actually thicker for most animals that I know of compared to humans.
Okay, so they would be, would you give folks a quick idea of the animal studies that you've already done, which?
Well, we do animal studies with hairless mice, which is not a typical pet at all. Although I must say they're extremely cute. But yeah, they're not really relevant to any animal pet that I know of.
Very good. Thank you. Thank you. There's a more general question which relates to the previous version of the Far UV white paper versus the current version of the Far UV white paper, and what's the consensus of the panel on public application of Far UV or using Far UV in public spaces? Should we, shouldn't we? What's the general consensus? I'm going to start with David Sliney as our safety expert, and then pass it over to Karl and Chip.
Well, from a safety standpoint, every study clearly demonstrates it to be considerably safer than 254 nanometer mercury line. But I guess we'll have to wait until there's some studies of actual installations to be sure that there's no problem or complaints that are not clear from the basic research studies.
So we've got the basic research. We don't have the application studies so far. Is that
right? Right. In other words, confirmatory studies to put everybody at a sense of comfort that there's no potential hidden problems, but it's certainly based upon the current knowledge, it's can be installed quite safely.
Okay. David Brenner, Chip, Rich, Karl?
I guess one way of looking at it is, I mean, in all aspects of the medical or the biomedical world, we are talking about risk benefits, and that's go to any procedure in a hospital, and that's basically what you're talking about. So it's not a question, I think, of saying is the risk zero. The question really is what are the benefits, and what are the, if one's being very conservative, what are the absolute worst possible risks that one might think about? And it's that balance which is really, I think, the issue with.
Yeah, maybe if I could just build on both David's and their comments, which are, I think, right on. Just backing up a little bit, there was an earlier version of this white paper that was produced, and I was one of the authors of that paper. We received legitimate criticism of that paper, and that's part of what motivated the generation of this task force. And the idea of the task force was to be broader in terms of the expertise that we brought in, and really to address some of the concerns that were expressed with respect to the first version of the white paper. So full disclosure, we stepped back and invited people to join us in preparing version 2 of the white paper that provide a more comprehensive view of the information that relates to this. So, I mean, I would invite Rich and Karl also to comment on this, but I mean, I think the way David Sliney and David Brenner have summarized kind of where we are and the potential for this, I think is spot on. I think it shows great promise, but probably requires some clinical studies to look at, you know, how it actually works in a field setting.
Okay, good.
I can just chime in there, Troy, real quick.
Please, Karl.
We've done some work. There's actually some applications of Far Uvc technology out in the public already. People may have read articles and such. We worked a little bit with the Space Needle in Seattle. They have put in Far Uvc in a number of applications, and just to measure kind of the irradiance levels that they're achieving with their different devices that they've put out with Far Uvc. And they've also done a lot of work with UVGI, upper room germicidal with UV in air ducts and things like that that are also very effective, obviously, as well. And the thing that we saw when we did some measurements out of their units was that actually the UV fluence levels were very, very low. Like it was much lower than we thought they should be for one to achieve good disinfection. So maybe the systems are almost ineffective, and things. Some certain products out there may be less effective than others in terms of how long you spend under the light, and is it going to achieve an actual fluence that does much for disinfection. That's why we wanted to really quantify the dose response of these viruses and seeing what kind of doses you need to deliver to achieve effective applications. But as Chip mentioned and David, David's mentioned that, you know, we really need to do these clinical studies so we could see, is there a reduction in infection, transmission, in survival in actual field studies, and we haven't seen that yet or been able to do that yet in an extensive way.
Yeah, and just as Karl said, actually measuring in application is an important part of an installation. I don't think we should be looking at this as a carte blanche or a magic bullet, just Far Uvc everywhere in whatever levels, understanding how to have a sensible, reasonable application of the technology. It appears to be incredibly useful. It appears to be far safer than I certainly thought. And I was one of the authors with Chip on the original white paper. There's a great deal of evidence to say that this is a useful and effective technology, but it definitely needs to be applied in a reasonable and sensible way. Everything has its limits, and we're starting to learn that the limits of this technology, the safe limits, are in a window where we can find some application.
But if I can chime in more, I guess, a bit philosophical standpoint from technology development, this commonly used so-called TRL, technology readiness level. So I think Far Uvc is just another example following that the TRL. You know, I think this task force, the focus has been really go through the literature to demonstrate what we know, what actually we don't know. I think it's very much, you know, from the science and looking at the trends and look at a little bit prediction and the surrogates. I really enjoy many parts, but specifically, I think identify a couple candidates for surrogates. That's really allowing us to do the research properly to answer some of the questions I think the audience asked. For example, the effectiveness, of the saliva or the liquid layer, and all those things, I think can be properly addressed using surrogates and answer those questions quite easily. And then moving forward into applications, and I think that will, depending on the technology providers, to follow the rigorous kind of TRL from the proof of concept to scaling up to integrating in the system and testing, validation, approval, all those things. I don't think it's anything unique about this technology, but it's just how you bring the right technology in a robust way and to the public.
I'm going to bring up, this is a question that was not asked, but it's out there. We have all seen recently on news broadcasts, folks touting brand new technology that includes disinfection portals, walk-through portals, and these oftentimes are shown using CRL lamps, comparable lamps. Anybody want to comment on disinfection portals and things that are designed to directly expose people as opposed to exposing air or surfaces?
I could take a crack at that.
Please, David.
The issue with a portal is that as you walk through it, you're going to spend a very short amount of time there. So the amount of UV fluence or exposure that you're thinking about is going to be very small indeed. So I think that's the issue. So most of the thinking is these days is in terms of downlights, simply installing the Far UV lights in the ceiling.
There's another consideration about what are you trying to achieve with the portal? What's the purpose of it? Largely, it seems as an intent to inactivate any of the viral particles that may be on someone's clothing or their hands or their skin. Okay. If we're considering respiratory viruses, the virus doesn't live in your hands or your skin. It lives in your lungs, it lives in your nose, it lives in your throat. These parts aren't going to be hit by a Far UVC portal. They're not going to be hit by anything. You can wash your hands 1,000 times. It won't stop you from being infectious with COVID. So it's about an intent of what you're trying to do with the technology in terms of stopping COVID-19 or impacting the pandemic. I don't have much faith in portals.
Very good. Very good. Thank you.
If I could add to that, I think that the biggest opportunities for this technology are in crowded spaces where many people meet and have a chance to exchange viruses and diseases. That's where we need effective help. I wouldn't even call it a solution because there's no guarantee that Far UVC will really suppress, but it will lower the infection risk. Also, we don't have actual data yet, but the main thing is it should be first applied foremost where many people could meet, where you have exchange. And since it gives an opportunity to clean surfaces and air, I think it is a good technology that should be tried.
I might add a little bit too. I think part of in the application side, as you know, there have been several companies developing and implementing this over the last handful of years. You know, we've tried to learn from our predecessors, and that includes the people here in the water who were in the water space, and it includes a lot of the UV for the upper room that was predominantly focused on, you know, air changes and air change equivalents. And, you know, it's not a hard jump to basically use fluence assumptions and use the same calculations in the physics to get to some of those calculations in the space, knowing that then there's a natural evolution to going into the whole room space while following the TLV guidelines, you know, for safety and efficacy. And like Ted mentioned, there are still some unknowns, many of which, have been brought up on this. But I think there's a pretty sound body of knowledge that says this can be effectively and implemented.
Very good, PJ. Thank you, sir. I've got a slightly different question here. We've talked a lot about 222 on viruses. Karl, what's the impact of 222 on bacteria and molds? And carrying that forward, what does it do to houseplants? I mean, they're kind of related.
Well, certainly UV 222 is going to be effective against bacteria and molds. I haven't seen many study on harmful molds, but I imagine the mechanistic reasons why it's effective against other microorganisms would make it also effective against molds. But certainly against bacteria, we've studied many different viruses and phage and different organisms as well as protozoa. And UV is certainly effective at 222 as well as 254. I think the relative effectiveness may differ depending upon the organism. For instance, we didn't see much impactful higher levels of inactivation under 222 for Cryptosporidium and Giardia, which are common waterborne protozoan pathogens, compared to 254. They're very similar in activation, but no enhancements there. As far as plants go, that's a really interesting question. I mean, plants respond differently to UV light as far as their life cycles and their respiration. They may be affected differently. Maybe somebody else on the panel knows more about plants. haven't studied plants, but it'd be very interesting to know more about that.
Karl, there is a correspondence between the stratum corneum and what plants' leaves have, which is a waxy layer at the surface of the leaf, which would also be protective. I might say at Columbia, we started with 222 more than a decade ago. And at that point, we were much more thinking about bacteria than viruses. And all our early studies were on MRSA, and certainly is effective against MRSA. And the very nice thing in that context is that UV really doesn't care about drug resistance versus drug sensitivity. So it was designed initially, or thought of initially, as a way to get around the issue of drug-resistant bacteria. And I think there's still a lot of promise there in the field of surgical site infections.
Very good, very good. I'm going through. There's several questions that come up when we talk about public areas. There are different types of public areas. There's lobbies, obviously. There's conference rooms, classrooms. There's bathrooms. There's individual offices. Any comments on the applicability of Far UV to any of these spaces? Are they all equally opportunities to be candidates, or are some better than others?
I would echo Holger's earlier comment that really the issue is crowded spaces, and it's when people are fairly close together and ergo their breathing is close together. So anywhere where people are in close proximity to each other, and theaters and restaurants are good examples of that, would be, I think, more useful than scenarios where people are not so crowded.
Yes, David, if I could maybe modify that a little bit, at least the way that I think about it is that I think the greatest potential for application is in facilities where there's the high potential for disease transmission. So, I mean, if you have highly infected people, for example, in a clinical setting, the demand there or the benefit there might be greater than it would be in some other settings. But so I really sort of view this as a barrier against disease transmission. It's an imperfect barrier like most, but it's one that could be effective in many different settings, elevators, classrooms, boardrooms, whatever.
I think I agree with everyone else.
So
I'm sorry that I think it is I agree with everyone, but one thing I want to mention about here is that even viral load is very important. Actually that is proportional to the crowded spaces, and in each spaces of application require some certain amount about the irradiation level or TLB level, under the TLB level, that under the guidelines that we should be meet that goal, and then maybe that in the guidelines that we should be designed very carefully each applications, that how much that light intensity require, what kind of a position of the lamp should be, those kind of things will remain as a kind of future application considerations.
If I could add to that, from my knowledge, all reputable manufacturers of Far Uvc lights will only deploy into controlled industrial environments or commercial environments, where the light levels or the UV levels will be carefully planned, predetermined, and measured after installation. I do not foresee and I do not recommend to widespread Far Uvc sources into home use or uncontrolled and unplanned environments.
And Holger's comments really tie in. I think we've been saying a lot in this panel about it's about the right application of the technology. It isn't, as a group, we're formed to review the scientific and the literature basis. What's the current state of knowledge of Far Uvc? I think it's the title of the paper. We weren't formed to review the ins and outs of the applications on how to actually build solutions with Far Uvc, more saying this is what we know about this technology. And it all comes down to now the next question is how does it get applied? I think it come up a couple of times, and Chip noted about whether you're looking at a clinical setting where you have a high viral transmission risk. It's exactly the same as the importance of mopping the floor in a hotel lobby is very different to the importance of mopping the floor in an operating room. The risk of disease transmission is different between the two. This isn't a special form of technology, more so than bleach. There are ways of disinfecting. We have numerous cleaning methods. This is just an additional tool that has recently been developed and to be effective and safe. Now, how that's actually applied, that you need to take into consideration of what's the situation it's being used in. How is it being used alongside other techniques such as simple cleaning procedures, air exchange, etc. And then taking a controlled view, as Holger said, this isn't necessarily something that you want in a residential setting. If you have a building management service, looking at the holistic cleaning rota and schedule to reduce disease transmission in that space is a great way of employing technology.
Excellent summation, Richard. Thank you. Thank you. There's a question that's popped up a couple of times, and that is, I'm going to summarize it. Do the pathogens that we're trying to treat, do they ever build up resistance to UVC? Karl, would you like to start on that, or Chip?
I can start. Yeah, I mean, the types of damage that are caused by UVC are strong enough and significant enough that we haven't seen the ability of the pathogen to then mutate and correct for that damage, or actually develop resistance to that types of damage. I mean, at different wavelengths, it may be possible in the UVB range to maybe more encourage mutations versus the types of damage that lead to inactivation. That's my understanding. We've done some studies on generational resistance of bacteria, E. coli specifically. We haven't seen any increase in resistance of the microorganisms to UV over generations. There may be different data out there, different pathogens, different wavelengths, though, and maybe others have other experience with that. And maybe some evidence from what happens in skin can also be used here.
Chip?
I will really just kind of echo what Karl said. I think we've done similar studies. There are others that are out there. I don't think there's any evidence to demonstrate generational change in resistance to UV. Having said that, however, I will say that nature seems to be pretty sneaky about figuring out how to do that sort of thing. So the fact that it hasn't been discovered yet doesn't mean that it doesn't exist. But at least as far as I know, there is no evidence to demonstrate that yet.
One might add that we have been using UV light to disinfect and decontaminate for many decades, and no sign of that to date.
Yeah, fact is, it was really actively used back in the 30s and 40s to combat tuberculosis, and we haven't seen any genetic change in the tuberculosis, which would indicate it overcame the UV treatment going back almost 100 years now. Is that a fair statement? I'm seeing nods. Okay, that's good. That's good. Here's a question I definitely want to address. It's addressing the discrepancy in definition of terms, how the terms are used, fluence versus fluence rate, irradiance, fluence rate versus irradiance versus fluence, how these terms are used to formulate methodologies of measurement. A lot of confusion out there about what's the real way to do things, aka what are the standards out there. I just want to say, and I invite everybody else's comments, IUVA is trying to work with other associations who are key in this technology, specifically the Illuminating Engineering Society. We've just opened up an MOU with ASHRAE, and we're rapidly, as fast as we possibly can, trying to get standards into the industry consensus standard framework, ANSI, so that they're consensus-based standards that industry can sign up to. This includes the definition of terminologies, where we've got a standard about to be published for public comment on just how to measure the output of a UV bulb. So please stand by for information. We try to keep folks updated through IUVA.org and the UV Solutions magazine. And we're pedaling as fast as we can on that one, let me tell you. It's an important topic. Anybody else care to comment? Okay.
I just say it's probably a balance between, sorry, Karl.
No, go ahead. I was going to change the subject. Go ahead, Rich.
No, go ahead.
So
go ahead.
It might be a balance between the sort of more common term of UV dose and then the more accurate terms of UV exposure, radiant exposure, or fluence. And it's just the difference between the technical literature and what's used in the marketplace more generally. So.
Good point. Troy, I was going to suggest maybe we go back to the question about the filters, because I think one of the things about exposure is, the different wavelengths that are being emitted. And if we could eliminate those higher wavelengths to 258 or so, we can maybe increase the exposure levels we're allowed at 222 specifically. So maybe some of the manufacturers on the call can talk about the different types of filters, mechanisms that are used.
I could take a first stab at that. Yeah, I mean, they're definitely, especially as we consider moving up in the TLVs, the weighted amount of the 258 could be exceeded if the notice of intent to change from ACGIH is realized. And so the best way around that is to actually use filters to block out those higher wavelengths. In addition, some of the filter development can also help on the lower end. in blocking out wavelengths below 200 to minimize potential ozone creation. So I think there's quite a bit of development and opportunity around the continued development of advanced filters for Far UV, for sure.
Okay, two more quick questions. One is, could we get a real simple explanation about the inactivation mechanism of 222 versus the inactivation mechanism for 254? We talked about the DNA impact, but I'm not sure it's really been clear yet about the other inactivation mechanisms that come into play using 222. Karl?
Yeah, I can take a stab at that. My dog's yelping in the background, excuse me. So basically with proteins in 222, we're damaging the protein that typically would cause maybe the attachment of a virus to a host. And if we could interfere with that attachment mechanism, that can minimize the potential for the virus to attach to the host and therefore minimize the infection of that virus into the host. So one mechanism is looking at maybe damage to those spike proteins on the coronavirus or damage to the fiber proteins on other types of viruses. That can definitely lead to minimization of the virus's ability to attach to its host and cause an infection. So that's definitely a mechanistic area that we've looked at and we've shown as being effective. Compared to 222, could also damage the nucleic acids, which would be similar to the 254 damage of nucleic acids. We've definitely seen, compared to 254, the 222 has much stronger damage on the proteins. And this is measured through liquid chromatography mass spectrometry, looking at protein damage and protein denaturization, as well as gel electrophoresis methods. So those are the differences in the inactivation mechanisms specifically that are the general ones that look at, compared to the genomic damage versus the protein damage. We have the 254 and other wavelengths damaging the genome as well as 222. Then the proteins specifically are highly absorbing the lower wavelengths, which is what makes, I think, Far UVC very effective. One of the things we found with certain viruses that were showing to be quite resistant to UV, like adenoviruses specifically, we've shown that when you have low wavelengths, the addition of that protein damage can greatly lower the dose required for high levels of inactivation. So you get that synergistic effect of the protein and the nucleic acids being very effective combined for inactivation. I think that's very strong, but obviously for exposure in human occupied areas, we want to minimize the 254 exposure, maximize the 222, and luckily 222 is very effective on its own.
Very good. Thank you, sir. I've got a question that has popped up a couple of times, asking about the effectiveness of 222 nanometer lasers as opposed to more standard emitting sources. Rich?
Oh, I can maybe pick up. Yeah.
Yes, you can.
Yeah. So actually, the Krypton chloride laser is not surprising enough. Actually, the Eczema laser is kind of first commercial product in the industry in 1980s and 90s, and so the main reason of them is for the clinical uses, especially for the other application, not the disinfection application. But thing is that, so what does it mean is the technology is possible to making a laser, but as you know that because gas discharge tube is main design of the lasers at the moment, and so the size of the we call resonator, like the laser body itself, is a little bit quite volumier than is a larger volume than current lamp structure that is commercially available. So their practical use is kind of a issue. So that's why not being used, but technically it's possible, but it's not possible in commercial product as a disinfection source. And maybe pricing will be more, you'll be surprised by that.
Just to add to Sunjin's comment there on the viability of the source, there's also a practical application of how you would employ a laser for a disinfection application. Lasers, by their nature, produce a very small spot size. When we're talking about surface disinfection, it's all about area of coverage, how much of the surface are you hitting, and with air, how much air is flowing through the path of that UV light. The design of disinfection systems with lasers is challenging. If you want to try and spread the light around as much as you can. So it's yeah, not the best source for disinfection, unless you have a very small area to disinfect.
Okay, very, very good. How about the effect of the environmental condition on the effectiveness of 222? High humidity, low temperature, high temperature, atmospheric dust. Comments there?
Well, I could comment on the influences on the light source. The Krypton chloride lamps are by far not as dependent on temperature as mercury lamps, so they're fairly stable over the life, over the temperature. And the humidity has a minor effect. Of course, humidity can have a big effect when it comes to pathogen reduction, but Karl can comment on that. When it comes to UVC light, contamination certainly becomes a concern. So if you have a glass window or a filter in front of the lamp, and over time there will be some dust or other material settle on the glass surface that can change the output quite significant. That should be put into maintenance procedures in applications to clean those windows well and good from time to time.
Yes, I agree with that, Holger, that so far in my just experiment that I see that only humidity is kind of major impact to the pure transmission of IUVC at this moment, and maybe those kind of environmental cleaning up is this maybe another issue. Maybe that's very common to the every other UV wavelength, UV lamp, UVGI industry too. So I think that part is we share together.
Very good, very good. A couple of questions have come up about constant, the comparative efficacy between having a constant on 222 nanometer source versus a pulsed 220 nanometer source. There's some ongoing comparisons of constant versus pulse effectiveness in 254. Is there a comparable conversation going on in 222? Anybody want to address that one?
I think yeah. Go.
There has been a little bit of work in that area, and it doesn't really show any difference. So I will emphasize there's not that much that's been published in that area so far, but for the information that is available, it really doesn't seem to matter. Dose seems to be the master variable, at least focusing on coronaviruses. But for other organisms that might have a repair mechanism, then perhaps it could be relevant.
How does that apply when you talk about dose is the relevant thing? Does it make it a difference if the dose is rapidly applied in a very short time period, high intensity, or low intensity long term?
Again, based on available information and based on Bunsen Roscoe, no, it doesn't really make any difference over what period of time that dose is accumulated unless there's a repair mechanism. And again, for the respiratory viruses in general, there aren't repair mechanisms.
Okay.
And in actual systems, maybe we need to consider that because in those spaces usually we have air circulation, so those kind of dynamic change of the density of the virus or pathogens in a specific surface might be maybe need to be considered for those kind of pulse or just continuous operation.
Very good, very good. Here's a very specific technical question that I'm going to ask Rich to address. If we have a filter over the bulb to make sure we've just got the 222 and not ozone generating gases or emissions, does the filter degrade over time such that it's the filter itself is less effective?
Well, that's a pure question of the filter quality and the manufacturing process. From our experience, there is essentially no significant degradation over lifetime, over several thousand hours.
So usually, in general, it depends on who using what kind of filter they use. Very common filter being used in these days are based on the stack of the different ceramic materials, such as oxide materials, like in the metal oxide or the mineral oxide materials. Actually, they are very well known to be very ozone resistive. Of course, that I agree with Holger's comment on that. Depends on the quality of the being made, but usually material itself is not ozone subjective. So.
Very good, very good. Well, we've about reached the noon hour. I want to pass it around the panel for any concluding comments that you might like to share. And I'm going to address the whole panel. Let me start with Soon-Jin, please, sir.
Yes, I think so. I cannot speak for all the members of the task force, but we worked very hard. Actually, I want to let everyone know that we worked very hard every week, and lots of the time and effort being to accommodate many questions available in these days about Far Uvc. And main motivation of this technology being started hard is that due to the COVID-19, and we do using some labs already in public right now, and but we are approaching very carefully because the scientific and the technical part should be followed for that for the real use of the effective use of this technology. But I feel very comfortable that this technology is going to be a big potential for the future in the disinfection and any disease. We prevent any kind of airborne disease, something like that. So.
Thank you very much, Soon-Jin. PJ, sir.
Yeah, I think this was a great exercise in getting, really all the data out there in one place regarding the safety and efficacy. And I think there's a logical next step that, either this panel or others now have the ability to leverage on as we talk about the proper design, engineering, and application of the technology in the many places that were discussed. And so I think there's a lot of information out there. It was kind of beyond the scope of what we tried to tackle with this first effort. And I'm very excited to really get a lot more knowledge about that next step out there. And I think that there's a great opportunity to do so, not only in this panel, but for a lot of people hopefully listening as well.
Very good. Thank you, PJ. Ted, I'm going to ask you to give your comments, if you would, please, sir.
Yeah, I think the theme really came out from today's webinar, and lots of great questions. And then look at the participation level. It's probably the record level too. So I think I concur with PJ's comments around, I think this is just a start in terms of correlate the science and the knowledge we have. And we should keep in mind, product development, commercialization. It's another journey where I think the technology providers working closely with other stakeholders just need to follow pretty rigorous development process. I already mentioned that TRL level. And specifically, some of the lessons learned, again, be mentioned about UV applications in other areas like water and the air and so on, I think can all be applied. So we don't have to recreate or reinvent the wheel. Concepts like those distribution, concepts like testing validation, and using CFD modeling, using bioassay, a lot of tools in our toolbox have already been developed, tested. The last comment I want to make is also, we're still in pandemics. Like I'm in Ontario, Canada, we're under lockdown, and a lot of people are really affected. Particularly, I look at the kids, the youth. So we should keep the risk in mind and really think, how can we accelerate the adoption in a safe and rigorous way and make an impact? Thank you.
Very good, Ted. Thank you, sir. Going along, Rich. Really appreciate your comments today. Thank you, sir.
No worries. I think it's really echoing what most of the task force have already said. I mean, it was fantastic to be part of this group and to pull together the current state of knowledge and improve the messaging from the first iteration of the white paper. I think this is a great development. The current state of knowledge, I think we've really covered that well. Yeah, there's a lot of potential for this technology. I'm really glad to see the results and be able to talk to some of the other expert members of the group. Really brought a lot of experience and knowledge to this conversation. I think I've said probably enough now. There are no magic bullets. Everything needs to be considered in its proper application, but alongside other disinfection technologies, there's great potential for Far Uvc.
Thank you, Rich. David Brunner, please, sir.
Of course, I think the two real issues are safety and efficacy. So in terms of safety, and the amount of literature that's out there now is really pretty convincing, and do encourage the participants to look in the white paper. Efficacy is a harder story because obviously it's easy enough to do those, relatively easy to do some sort of studies in the laboratory, but to do efficacy studies in the real world is really very difficult. To do epidemiological studies is well and nigh impossible, and you can't introduce viruses artificially into the public environment. So while efforts are going to be made in that direction, we perhaps need to rely a little more on the simulations that are now becoming very sophisticated, the computational fluid dynamics, the CFD simulations, which really, I think, do give us a pretty good impression of what the efficacy of this technology is going to be.
Very good. Thank you, David. Holger.
The
please,
optical
sir.
models, David. Optical models, or
Holger.
Yeah, I can only say I'm very honored to work with such a fine group of experts for the last couple months, and for anyone on the outside, we didn't take it easy. We had our internal strong discussions. We tried to choose our wording in the final document very, very carefully. I think we have come to a conclusion that we definitely think it is worth to look at this, basically new technology. And as we heard even today, there is still many open questions. Some are probably easy to answer. Some should be answered by the science community. And I can only encourage anyone out there, keep asking these questions, and especially keep looking for answers to these questions. That's how we make progress.
Very good, Holger. David Sliney, wrap up comments, sir?
Well, unfortunately, my computer went down and I lost the last few minutes, but I gathered we're talking about the experience with the task force. I thought it was very useful effort, and I was very impressed with all the wide-ranging expertise that was brought to bear by the group.
Very good. Thank you, David. Karl.
Thanks, Troy. Thanks to the panel as well. It's been great working with everyone on this panel. I think for me, the exciting part is following the science and really learning more about the human exposure side of things, given that I focus mostly on the disinfection side. But what's exciting to me really is to see the overlap of the TLVs that are allowable exposure levels, that these definitely overlap with effective disinfection of viruses. And the fact that these two overlap gives us great potential to be within the current knowledge state, really apply UV technology like 222 to be effective for disinfection while staying under those threshold level values that we've seen before. And if these values even go up higher, we have even more leeway to apply this technology in public spaces effectively and within the current guidance. So I think given those two things, it's really exciting for me to be part of this group and to contribute to that science and hopefully see applications. And as David Brenner mentioned, we need to see the effectiveness studies in the field to match the efficacy studies we've been able to do in the lab. And with that marriage, I think we'll see a lot more applications coming out.
Good stuff, Karl. Thank you, sir. Chip.
First, thanks, Troy, to you and Mickey for doing a great job of coordinating this webinar. I think it went off really well. I appreciate your effort in doing that. And thanks also to the task force. This has been a great group to work with, and we still have a lot of work to do. So you're not off the hook yet, but anyway, I've learned a lot by participating in this group, and I hope others have as well. So this technology, not to beat a dead horse, I think this is a technology that is, at least to some extent, being overlooked right now in terms of its potential to improve the situation with respect to the coronavirus or more generally airborne pathogens. And I think we need to take the next steps to make sure that this technology is implemented in a way that's safe and effective. Part of that, I think, will be engaging the regulatory community in discussions about this. So my hope is that one of the outcomes of this webinar is that we can have some serious meetings with people from the regulatory community in the US and elsewhere about how this might be done. And we also need to be having similar meetings with research organizations, federal agencies or whatever to support the clinical work that's been described by several others already. So again, this is a technology that has great potential. We need to make sure that we don't stop here. We need to do the next steps.
Very good. And Chip, thank you for chairing this. Your leadership has really brought things out and resulted in good products. So kudos, my friend. Good stuff. With that, as facilitator, I get the pleasure of saying we're done. Thank you very much. Watch the website for the slides, the videos, and follow on action. Thanks to all the audience for joining us. Love your support. Be safe, be well. We're out.
Thanks, Troy.
Thank you all. Thanks, Jeff. Thanks, Troy.